Welcome to The Deep Dive. Today, we're tackling something really fundamental in the big data world. How do you actually chop up these massive data sets so they perform well and can scale up?
Yeah, it's crucial.
Especially if you're working with distributed systems or, maybe aiming for a senior engineering role, understanding data partitioning is absolutely key. Think of this as getting equipped with the knowledge you need to talk confidently about dividing and conquering data.
Exactly. We're going to dive into the main strategies for partitioning key value data. The goal is really to distill the important concepts, give some insights that go, well, beyond just definitions. We'll look at why certain ways are chosen, the trade-offs, all that stuff.
Okay, and we're focusing on two main methods today, range partitioning and hash-based partitioning.
Right. Those are the workhorses, you could say, behind a lot of large-scale systems.
And understanding the nuances, it's not just theory, is it? Okay, so let's really get into it. Where should we start?
Let's kick off with range partitioning. Imagine a print encyclopedia, the old kind, divided into volumes, AC, DF, like that.
Right, okay. So if you're looking for Kafka, you know not to look in the AC volume. It's organized into these continuous chunks.
Precisely. And databases do something very similar with range partitioning. Continuous ranges of keys get assigned to specific partitions.
So all the data for keys in, say, range 1 to 1,000 lives on partition 1, factored 1 to 2,000 on partition 2, and so on.
Exactly that. The big advantage is efficient retrieval because you know exactly which partition has the data just by looking at the key.
Makes sense.
Plus, you can hit different partitions in parallel, which helps performance, and it breaks a huge data set into, well, more manageable pieces. Systems like Bigtable, HBase, RethinkDB, even MongoDB before version 2.4 use this approach.
So it's about keeping things that are close in key value together. And often within those partitions, the keys are actually kept sorted, aren't they?
That's a key point, yes. Keeping keys sorted within each partition enables really efficient range scans.
Ah, okay. Like if I wanted all sensor readings between 9:00 a.m. and 10:00 a.m.
Perfect example. If your key includes the timestamp and the data is range partitioned by that timestamp, you can hit maybe just one or two partitions and scan through that specific time range very efficiently.
Sounds great for ordered data like time series. But what's the catch? There's usually a catch.
The main one is the risk of hotspots.
Right.
Think about using timestamps as keys again. If all your new data has current timestamps, all the incoming writes might hammer a single partition, the one holding the latest time range.
Ouch. So one part of your system is sweating while the others are just chilling?
Exactly. That partition becomes a bottleneck, and you lose the benefit of distributing the load. It's a common issue with sequential keys.
Okay, that sounds like a real problem. How do you, try to work around that with range partitioning?
A common strategy, especially for timestamps, is to add a prefix to the key that spreads things out more. Like instead of just timestamp, you might use sensorid.timestamp.
Ah, so even if the timestamps are sequential, the different sensor IDs would hopefully land writes on different partitions.
Precisely. Writes from sensor A go to one place, writes from sensor B to another based on that prefix, even if the timestamp part is similar.
But then if you want data across all sensors for a time range, you have to query multiple ranges, one per sensor.
That's the trade-off, yeah. It makes some query patterns a bit more complex. You solve the right hotspot, but might make certain reads slightly more involved.
Okay, makes sense. So let's say I'm in an interview, senior role. How should I explain range partitioning effectively? What do they want to hear?
Well, first, explain the core idea clearly. The encyclopedia or card catalog analogy works well.
Okay.
Then hit the benefits. Efficient range scans, parallel access is good, manageability. But crucially, you must talk about the hotspot problem, especially with sequential keys.
Right. Sure. You know the downside.
And explain mitigation, like key prefixing, and acknowledge the trade-offs that introduces. Mentioning systems like Bigtable or HBase shows you know where it's used.
Good. Any tips?
Yeah, a good tip is be ready to discuss real-world scenarios. When would range partitioning be a good fit? When would it be a bad choice? Think access patterns.
Solid advice. Okay, let's switch gears. The other big one, hash-based partitioning. I'm guessing this tackles that hotspot issue.
That's often the main driver, yes.
Yeah.
Hash partitioning takes a totally different approach. Instead of using the key's value directly to decide the partition,
You mash it up first.
you run the key through a hash function. The output of that function, the hash value, determines which partition the data goes to.
Okay, so it's like putting the keys in a blender, and the random-looking output tells you the destination shelf. Even if my keys are 1, 2, 3, 4, the hashes should be all over the place.
Exactly. A good hash function gives you a nice uniform distribution, even for sequential inputs. So your data gets spread much more evenly across partitions.
Ah, so those timestamp keys we talked about. If you hash them, the writes should distribute nicely.
Correct. The resulting hash values will likely fall into different partition ranges, spreading the write load and significantly reducing that sequential write hotspot risk.
Nice. Which systems use this?
Quite a few. Cassandra and MongoDB, for instance, use MD5 hashing for this. Voldemort uses a different one, Fowler Nolvo.
Okay. Now, I've definitely heard the term consistent hashing used around this stuff. Is that the same thing or something different?
It's related. Consistent hashing is a form of hash partitioning. It was originally designed with a specific goal, minimizing how much data you need to move around when you add or remove servers in your cluster.
Ah, okay. So it uses hashing, but the consistent part is about making scaling smoother.
In its original formulation, yes. It uses some clever tricks with pseudorandom partition boundaries on a ring, typically. It became popular with content delivery networks, CDNs, for caching.
So less shuffling of data when nodes come and go.
That was the main idea. However, and this is important for clarity, especially, if you're talking about this in interviews while the term is well known, using that specific original consistent hashing algorithm as the main partitioning method in many modern databases isn't as common as you might think.
Really?
Yeah, the core principle of minimizing data movement during rebalancing is super important, but the specific mechanics vary. Sometimes, trying to explain the original consistent hashing ring in detail during a general partitioning chat can just muddy the waters.
Ah, okay.
It's a bit of an IT joke, right? Trying to explain consistent hashing sometimes feels like you're trying to achieve distributed consensus just on what the definition is.
I can imagine. So, interview advice. Probably best to just call it hash partitioning unless specifically asked about the consistent part.
Pretty much. Focus on hash partitioning for distributing data and avoiding hotspots. If consistent hashing comes up, you could say it's a type of hash partitioning known for helping with efficient rebalancing, especially in dynamic systems like CDNs, but maybe don't get lost in the weeds of the algorithm itself.
Got it. Keep it focused. Okay, so hash partitioning is great for spreading writes. But what did we lose? We lost those nice range scans, didn't we?
Bingo. That's the major trade-off. Because the data is scattered based on the hash of the key, the original key order is gone. If you want to query a range of keys, like users 1,000 to 2,000.
You can't just go to 1 or 2 partitions anymore.
Right. You likely have to ask all the partitions, hey, do you have anything in this range? Which can be much less efficient. Systems like React, Couchbase, Voldemort, when hashing the primary key, often don't support efficient range queries on that key for this reason.
And MongoDB.
With MongoDB's hash-based sharding, range queries typically have to be broadcast to all shards. Again, potentially less performant than a targeted range scan.
So if you do a lot of range lookups, maybe hash partitioning alone isn't ideal. Are there ways around this? Any compromises?
Some systems get clever. Cassandra is a good example with its compound primary keys.
How does that work?
Okay, so the first part of the primary key is hashed. That determines the partition, giving you that nice even distribution.
Right.
But then the subsequent columns in that primary key are used to sort the data within that partition.
Ah, so you get the distribution benefit and local ordering.
Exactly. So if you know the value for the first part of the key, the one that was hashed, you can go straight to the right partition and then perform an efficient range scan on the second part of the key within that partition.
Can you give an example?
Sure. Think social media posts again.
Yeah.
You might have a primary key like the user id, update timestamp. Cassandra hashes the usered. So all posts for a specific user land on the same partition, nicely distributed by user.
Okay.
But within that user's partition, the posts are sorted by update timestamp. So if you want to get, say, the last 24 hours of posts for user 183, you find their partition using the hash of user, then you do an efficient range scan on the update timestamp within just that one partition.
That's pretty neat. A good compromise. Okay, but we talked about hashing helping with like sequential timestamp hotspots. What about a different kind of hotspot? Like one celebrity user posts something and suddenly everyone is trying to access or comment on that specific post. The hash of the post ID is still just like one hash value, right? It still goes to one partition.
You've nailed a really important limitation, yes. Even with perfect hashing, if your workload is massively skewed towards interacting with a single key, that viral post ID, you'll still get a hotspot on the partition responsible for that key. Hashing distributes keys, but it doesn't magically split the load for one incredibly popular key.
So hashing isn't a silver bullet for all hotspots. What do you do then?
In those extreme cases, the fix usually has to happen at the application level. It's not something the database partitioning itself can easily solve.
Meaning the code using the database needs to be clever.
Right. A common technique for known hotkeys is to add some randomness or variation to the key before writing. So instead of just writing to a post-to-WEAK, your application might write to 01.post-to-WC, 02.post-to-WC, 03.post-to-WC, maybe choosing the prefix randomly or round robin.
Ah, so you're artificially splitting the writes for that single logical item across multiple actual keys.
Exactly. Those different keys will likely hash to different partitions, spreading the write load for the hot item.
But then reading it back must be more complicated.
Yeah.
If I want all comments for posted.wc, I now have to know to look for 01.posted.wc, 02.posted.wc, etc.
Precisely. You push the complexity to the read path. Your application needs logic to know how these keys were split and query all of them, then aggregate the results. It's a definite trade-off. You get better write throughput for the hot item, but reads become slower and the application logic gets trickier.
Yeah, that highlights that you really need to understand your specific data patterns, doesn't it?
Absolutely. Even with smart partitioning, understanding and adapting to access patterns is key.
Okay. So, interview time again. How do we summarize hash-based partitioning?
Explain, it uses a hash function for even distribution, great for mitigating sequential key hotspots. Give examples like Cassandra, MongoDB,
Okay.
but immediately follow with a trade-off. You lose efficient range queries on the hashed key. Then, mention compromises like Cassandra's compound keys. And importantly, acknowledge it doesn't solve single key skew, explaining the application-level workarounds like adding prefix exegesis and the complexity that adds.
Got it. And the tip?
The tip is, always think about your application's access patterns. Are range queries critical? Is write distribution the absolute priority? That guides the choice.
Excellent. Okay, let's just quickly loop back to rebalancing. We mentioned it with consistent hashing. When you add or remove nodes in your cluster, you got to shuffle data around, right? How do these partitioning strategies affect that shuffle?
Right, rebalancing is fundamental. Doesn't matter if you chose range or hash, when the number of nodes changes, you need to redistribute data to keep the load fairly even. Otherwise, why add more nodes?
So even with range partitioning, where things seem neatly divided, adding a new server means you have to carve up some existing ranges and move data.
Exactly. You typically split some existing ranges. Maybe partition C gets split, and the second half moves to the new node. Removing a node means its ranges have to be merged into neighbors, and that data moved. The big challenge is doing this move with minimal disruption to reads and writes happening at the same time.
Okay. And with hash partitioning, where data is scattered based on hashes, how does adding a node work there? If the number of partitions changes, doesn't that mess up where all the hashes should go?
With a simple hash partitioning scheme, yes, that can be disruptive. If you hash a key and take the result modular n, the number of nodes, changing n changes the result for potentially most keys.
So lots of data might need to move.
Potentially, yes. And that's where the idea behind consistent hashing really shines. Even if the original algorithm isn't always used directly, its goal was precisely to limit that blast radius, to ensure that adding or removing one node only required a small fraction of the keys to be moved.
So the principle of minimizing disruption during rebalancing is key, regardless of the exact method.
Absolutely. Modern systems, whether primarily range or hash partitioned, have sophisticated mechanisms to handle rebalancing as smoothly as possible. It's a complex operational necessity.
So if an interviewer asks about consistent hashing's contribution to scalability,
You talk about its focus on minimizing data movement during rebalancing. Explain that efficient rebalancing is crucial for scaling distributed systems smoothly, allowing them to add or remove capacity without major upheaval. Good tip here. Show you understand rebalancing is a challenge, and that partitioning choices impact how hard or easy it is.
great insights. Okay, so let's try and wrap this deep dive up. We've looked at range partitioning, great for range queries, but watch out for hotspots. And hash partitioning better distribution avoids sequential hotspots, but makes range queries harder.
Right, and we saw compromises like Cassandra's compound keys,
Yeah.
trying to get the best of both.
And that concept of consistent hashing, even if not always the literal implementation, really points to how vital efficient rebalancing is when systems need to scale.
These are absolutely fundamental trade-offs.
Yeah.
Anyone designing or working with distributed data systems needs to grapple with them. The choices you make about partitioning directly hit performance, scalability, and how complex the system is to operate.
Definitely. So thinking about those trade-offs, query efficiency versus right distribution, the rebalancing headaches, what do you think? What kind of innovative partitioning strategies might we see next, especially for systems that are super dynamic, really high throughput? It feels like there's still room for improvement.
That's a great question to ponder. It's a constantly evolving space. And on that note, we'd love to hear from you, our listeners. What are some of the trickiest data partitioning challenges you've faced in your own work? How did you tackle them?
Yeah, share your experiences, your war stories, your insights. Jump into the comments or find our community forum. Your real-world perspectives are gold dust for everyone else listening.
Definitely.
Thanks for joining us for this deep dive. Until next time, keep partitioning those thoughts effectively.